In this video, I would like to introduce you to the concept of stoichiometry. Stoichiometry is a German word that has to do with or talk about the mathematical relationships that exist in chemical reactions. Okay, so that we can look at the quantities, the relationships of quantities, the amounts in a chemical reaction. It's a lot like cooking. Okay, it's a lot like baking and following a recipe. So the first thing we have to do is remember the concept of the mole. So remember the mole? Not that guy over there. 6.02 times 10 to the 23rd, 602 heptillion particles. Whatever it is, its mass in grams is that element's value on the chart. If it's a gas at 0 degrees Celsius and 1 atmosphere of pressure, it takes up 22.4 liters of space. That's a mole. We're going to bring that concept and combine it with the other concept of balancing chemical equations. Remember, an equation tells the story of a reaction. It tells you what goes in, the reactants, and as a reaction takes place, what you get out, the products. And it has to obey the law of conservation of mass. What goes in has to come out. It may come out rearranged and in a different form, but it still has to come out. So we have to balance a chemical equation so as to follow that rule, to fulfill that rule. So we use coefficients, right? We use numbers in front of formulas. We can't change formulas. We put numbers in front of formulas to balance equations. It turns out that not only can we relate to that on an atomic level, 3 atoms over here, so I got to do something to make sure there's 3 atoms of the same thing over here, no matter how it's combined in a different formula, the different subscripts. We can also talk about that, those same numbers that we use to balance it, on the scale of moles. So we use the coefficients to balance, and then that tells us the molar ratio, the proportionality, how much of each thing there is going into the reaction and getting produced by the reaction. So the example I have here, sodium sulfate, calcium chloride, I'll get calcium sulfate and sodium chloride. Right? It's a double replacement reaction. Based on the formulas, I end up with 2 NAs and 2 CLs, but since Na and Cl go together in a 1-to-1 form, I need 2, or I'm going to produce twice as much sodium chloride as I do either sodium sulfate or calcium chloride that's there. Okay, so when I balance it, it's a 1, a 1, a 1, and a 2. And those numbers are ratio. I can use them now as ratios to relate any two things in that equation. Once I balance it, I know all the relationships, and now I can look at any two that I need to. So, for example, in this particular equation, there are 6, really 12, molar ratios I can make. Now, why did I say really 12? Because each one of the ones that you see here, I could also flip it upside down. What's important is not just the number, but the label that goes with that number. And it's really important to take the time to keep the label and write the label so you know what it is you're talking about. So you know whether you've got your fraction, your ratio lined up the right way or not. So how do we use this? Let's say I have on hand 8 moles of sodium sulfate, and I need to know how much salt I'm going to make from that if I have enough calcium chloride to make it all go away, make it all become salt. Okay, so I'm given 8 moles of sodium sulfate. How does that relate to the sodium chloride? Well, in the equation, there's a 2 in front of the NaCl and a 1 in front of the Na2SO4. So that's the ratio that I use from the equation. Notice the labels tell me which way to put the fraction. If I'm starting with Na2SO4, I want that to cancel out. So I want that to be on the bottom. I'm trying to find sodium chloride. That's the label that needs to be on the top of the fraction. And if I put the number that goes with the label, I'll always put the number in the right place. I'll always do the right math, and I'll always get the right answer. The labels will lead you. Labels never lie. So Here's one for you to try. Balance the equation. Simple. Water. H2 plus O2 gives you H2O. Take a minute. So get out your pencil, paper, calculator. Balance the equation. For practice, write the different molar ratios. Once you get the hang of this, you're not going to have to write them all. You're just going to look and say, what am I talking about? What was I given? What am I trying to find? And that'll be your ratio. But for practice, write the molar ratios that are present. And then here's your problem. Hey, if I have 5 moles of H2, if I have plenty of oxygen, and all that H2 becomes water, how many moles of water will I produce? Pause the video and give it a try. All right, did you do that? Did you pause it? So here's your answers. 2H2 plus O2 gives me 2 H2Os. All right, because the O's are not the same, I need 2 H2Os to balance the O's, which means now I need to go back and put a 2 in front of the H2. Well, that means that for every 2 moles of H2, I need 1 mole of oxygen. And I'm going to get 2 moles of water. And for every 1 mole of oxygen, I'm going to get 2 moles of water. So, if I'm starting with 5 moles of H2, in this case it's a 2 to 2 ratio, water to H2, which means it's a 1 to 1 ratio. So, I'm going to end up with 5 moles of water. Okay, in the real world, we put things on a balance, or we measure their volume. And so we don't just have moles, we have to determine its mass. And once we have its mass, we can figure out how many moles, right? So if you know the mass in grams, and you get your periodic chart, you can figure out the molar mass for that compound, and then you can know how many moles or what part of a mole you have. So for this example, if I have 5 grams of pure sodium, well, on the periodic chart, 22.9 something other, I rounded it to 23 grams of sodium for every 1 mole. So to figure out moles, I'm dividing by the grams. And to figure out 5 grams of sodium, well, that's about 0.21, a little under a quarter of a mole. Now, let's say I wanted to say how much chlorine gas, how many grams of chlorine gas do I need to turn all 5 grams of sodium into sodium chloride? Well, the first step is I have to get moles, because I can't relate any two things in a reaction until I'm talking about moles. So the first step is convert to moles. Then the second step is I can look at the equation and figure out the ratio. What are their proportions to each other in terms of moles? So here's your equation. 2 moles of Na plus 1 mole of Cl2 gives me 2 moles of NaCl. So if I have 0.217 moles of sodium, again, notice where the labels go and therefore where the numbers go. I'm trying to find chlorine gas, so that has to be on top. I'm starting with sodium, so I need the ratio value from the equation, not the number I just did math with. The ratio value, in this case the 2, I need that on the bottom. So then I take what I have, 0.217, and in this case I cut it in half. So I need half as much chlorine. Okay, but I don't have a way to measure that out in a lab in moles. I have to put it on a balance again. So I have to convert that back to grams. So I multiply by its molar mass. Chlorine, the atomic mass of chlorine is 35.45, 35.5, let's say. Since this is diatomic, Cl2, then that's where the 71 came from. And so I need 7.72 grams of chlorine gas to take 5 grams of sodium and turn it all into salt. Again, here's an example for you to try. I balanced the equation for you. If I give you 2.5 grams of potassium chlorate, a solid rocket chemical, because it produces oxygen. So as it decomposes, it produces oxygen. And you see the values there for the balanced equation. So if you start with 2.5 grams of KClO3, what volume? Pay attention. I turn the tables a little bit on you. What volume of O2 at STP would be produced? So that means your third step, you're not going to be using molar mass. You're going to be using 22.4 liters because we're asking you for liters. But again, take your pencil out and your paper, grab your calculator, your periodic chart, and pause the video. All right, I hope you tried it because, I can't do the push-ups for you. You got to do the practice. Here's your answers. 2.5 grams, add up the molar mass. I come up with 122.5. If you came up with a little more detail, maybe your numbers are just slightly off, but that's fine, or slightly different, I should say, not necessarily off. But about 0.02 moles of KClO3. From the equation, it's 3 moles of oxygen I get for every 2 moles of KClO3 that degrades. So that means 0.03 moles of oxygen is what's produced. And at STP, that would occupy about 2/3 of a liter, 0.67. So hopefully you get the hang of the idea here. It's a three-step process, thinking process. Now, you get the hang of this and you think it through, you can always just think, hey, what fraction am I going to need to do first? And then what's the molar ratio? And then how do I get to my answer? And you could line it all up in one kind of sequence of things and then just multiply by what's on top and divide by what's on the bottom. But I broke it out as individual steps for now so that you see the process. And hopefully this is a good resource and helps you to be able to solve all the stoichiometry problems that you come across.